Oh, hey, we're talking about friction now, and friction is due to forces between the two surfaces that are sliding, that are in contact, right? So you may have noticed it's harder to get something moving than it is to keep it moving, but eventually it stops. It used to be, people thought that an object's natural motion, a natural tendency was to be at rest, to be stopped. And then Galileo and Newton said, well, okay, if I slide this, it goes a ways before it stops. If I smooth the two surfaces, it goes even further. If I get an icy surface, it can go a long way. So maybe an object's natural tendency is not to be at rest, but to keep moving at the rate that it was started at. So it's going to keep moving. An object in motion tends to remain in motion until acted on by some other force. It's one of Newton's laws. So what's the other force? The other force is friction. As this surface is moving along, as the book is moving along here, there are electromagnetic bonds between this surface that are grabbing, little Velcro pieces that are grabbing up here, and there are electromagnetic bonds of these atoms grabbing down below. And so there is some kind of attraction between them. Also, if you get down to a small enough scale, this is not perfectly smooth. You know, you get down to the molecular scale, it's all bumpy and ridgy, and so is this seemingly smooth surface on a small enough scale. So now you've got bumps and ridges moving over each other, breaking each other. It creates a lot of lost energy as heat. If I rub this back and forth quite a bit, I can get heat, right? Just like you can do with your hands. So friction is a force. There's a frictional force. And it's due to and it occurs between the contact points of two sliding surfaces or two surfaces that aren't sliding. Like I said, it takes more to get something moving than to keep it moving, because if something's sitting still, it's got electromagnetic bonds that have had time to form between the two surfaces. Once you get it moving, you've broken those bonds, and now you're just worried about the smoothness of the surface. The electromagnetic bonds aren't as strong. But they're actual cold wells that you've got to break through. So it takes more energy to get it started than to keep it moving. Now let's talk about that force of friction. Called the frictional force. First piece of resistance, right? From now on, until we talk about energy, we're going to talk about different forms of resistance. And this is mechanical resistance, frictional force. And like any force, it's given by a capital F, and that little f means frictional. Now the general equation for the frictional force is that it's a coefficient. It's called the coefficient of friction, times capital N, which is the normal force. So mu is the coefficient of friction, and it has no units. It's dimensionless. The reason is, this is a force, this N is another force. It's called the normal force. By the way, the units for frictional force is force, so it'll be like newtons or pounds. Normal force is the same way. It's going to be like newtons or pounds. So if you got force here and force here, no room for any other units in the coefficient. Now the normal force, normal means perpendicular to. So the normal force is the force perpendicular to the surface. So if this is the surface, the force perpendicular to the surface is in this direction. Now you probably know that if I tilt something, if I have something here and I tilt my hand, then it's going to slide. The coefficient of friction didn't change, but the normal force did, because now here the normal force is being pulled down by gravity. As I go further and further down, there's less and less of a normal force. If I'm pushing here, I can slide my hand, but if I push harder, I increase the normal force, it's harder to slide my hand. Force of friction goes up with the normal force. Now, we don't have that much time to talk about all this. So we're going to assume, for this case, just horizontal surfaces. And also, we're not going to be pressing down. We'll just use the weight of the object as the normal force. So for example, this book I was sliding along, the normal force is just the weight of the book, or the mass of the book times the gravitational acceleration. Either way works. So I'll say for a horizontal surface, and not pushing down, just using the weight, the normal force is equal to the weight of the object, which is mass times gravity. Now, there are two types of coefficients of friction. There's the static coefficient. If it's not moving, cold wells form, and the static coefficient is higher than if it's moving, and that's the kinetic or sliding coefficient. So mu k, mu s, mu sub s, it's a mu, it's got that little hangy thing on the u, is the static coefficient of friction. Mu k is the kinetic coefficient of friction. You want to remember that the kinetic coefficient is always less than the static. It always takes more to get it moving than it does to keep it moving. You've probably felt that. You're moving at something heavy and it takes a lot to get it going, but once you get it going, you don't want to stop. You want to get it all the way over because it's a lot easier to keep it going.